Hi. So finally, what we're going to get to is using the Jacobian to evaluate a double integral, which might otherwise be, say, somewhat difficult to do. Okay, so first things first, we've got a region described here called R, and you can see it's bounded between these two sideways parabolas in the x-axis. So it might be nice to get a sense of what that graph looks like first. So let's go draw an xy axis. Here you go. One equation was y squared equals 4 plus 4x. And if I'm remembering correctly, the other one is y squared equals 4 minus 4x. Okay, so it might be neat to think about some of the points that this graph go through. So let's take a look at this bottom one for a minute. So if x were 0, for example, then what we would have y squared equals, say, 4. So then we would have y equals plus or minus 2. So that would correspond to this point here, and then further down the equal distance down below, maybe this point here. Okay, but we do know that this thing is also going to be bounded somehow by the x-axis, so we'll find out um, where. Okay, and then let's say we end up with, take a look at this top one. If we let x be 0, we also find out that y squared equals 4, so y equals plus or minus 2. So it's also going to meet up here and here. However, what about if y is 0? Well, in this case, on top, if y is 0, then you can see that you'd have 0 equals 4x plus 4. So that would mean x equals negative 1. So that means the graph goes here. And then also, if we did the same thing for the second graph, let's do it for this graph. Let's pretend y equals 0 there. In that case, we get y squared, well, 0 squared equals 4 minus 4x, and then x would just be 1 for that to work. So that graph would go over here. So what we start to see is we've got these parabolas which do something like this. So the red parabola is going to end up looking like that. The green parabola is going to end up looking like this. And now you can tell that the region we want to integrate over is between the x-axis and both of these parabolas. So it's this strange shape that we have up top. You can clearly see this is not a rectangular base region, which means that your double integral, whatever it looks like when we try to write it out, is not going to be like this. Here's a beautiful one. So let's say you had an integral just hypothetically, that went something like this, say from 1 to 2, and then 1 to 4, dA or dy dx. That would be nice because you don't have variable limits of integration, as opposed to this graph where clearly we can't say things like y always goes between, say, 0 and the same value, because we've got this upper parabola which varies. If we were to go horizontally with this double integral, then we would see that we vary from one parabola to the other, which may or may not be such a bad thing to compute. But it just so happens, if you go back to my other YouTube videos, I have one here titled, and let's make this a little bigger for you so you can see it, titled Transforming 2D Regions and Leading to the Jacobian. And in that particular video, we look at exactly this region and we apply a set of transformations. So when we apply that set of transformations, the transformations that you were asked to consider were x equals u squared minus v squared, and y equals 2uv. And when you're done, what ends up happening is this, or what we find out is that the region in the uv plane that is a perfect square with side length 1, that this region will map into the xy plane in such a way as to get the region that we have in this particular double integral. So we get this sideways red parabola, this sideways green parabola, and this. So it turns out that if we were to make this transformation of variables, if we apply this to this integral we're going to work on, then our limits of integration become really nice because the integral from 0 to 1 and the integral from 0 to 1 dA. So, and there's a y here. So as opposed to some variable limits of integration we'd have to use in this integral on the right, which is definitely going to have some, if you're going to have dy dx, for example, you're going to have some function of x here, some other function of x here, and then you're going to have bounds for x out here, which looks like -1 to 1. So it might be easier. This one's certainly looking more attractive at this point. So what we're going to do now is apply this transformation. Okay, so let's do that. Let's go to a new page here. We want to do the double integral of y dA, where x is equal to u squared minus v squared, y is equal to 2uv. And we already know that our limits of integration are going to be 0 to 1, 0 to 1. We're integrating y, so that's going to become 2uv. And then we have to pick an order. So why not just do this? We'll do du dv. And then what goes in here is the Jacobian. That's what's going to go in there. And so let's remind ourselves how we would do that. The Jacobian, we learned in a different video, we take the partial derivative of x with respect to u, and then the partial derivative of x with respect to v. And then we also find the partial derivative of y with respect to u, and the partial derivative of y with respect to v. And if we do these things and find that determinant, then we can sub that in right here, and our integral will have the correction factor it needs. Think of it like a correction factor, maybe like polar coordinates has a nice correction factor, same kind of thing. Okay, so let's do all the pieces. We're gonna let's use a new color here so we don't lose track of things. We're gonna take these things along with this matrix here. Sorry about that being so sloppy. Fix that for you. And apply it. So partial x partial u would be 2u. Partial x partial v would be -2v. Just in case you're missing this, up here is the u squared. The derivative is just 2u. And up here is the -v squared, so the derivative is -2v. On the bottom, I'm going to take the derivative with respect to u and v of y. So if u is the variable, the derivative becomes 2v. You can see that right here. If v is the variable, the derivative becomes 2u. And if you do the determinant of this matrix, just in case you forgot about determinants of simple 2 by 2s, you multiply these two together, so you get 2u times 2u. And then you subtract whatever you get when you multiply these two together. And that's going to be -2v times 2v. When everything's said and done, you just simply get 4u squared plus 4v squared. And this is the Jacobian, and that thing goes in here. So this is going to be 4u squared plus 4v squared. Sorry, I cut it off. So it's this part down here. This thing went up in the place of the Jacobian up in that integral. Okay, so now we're ready to do some algebra. Let's do that, just some integration and see what happens. Okay, so here we go. We've got the double integral from 0 to 1, 0 to 1, and we have 2uv times, and I'm going to factor out that 4 times u squared plus v squared. And the order we're going to choose is du dv. No particular reason here. I don't think there's an advantage. So what can we do? We could take this 2 and a 4 and factor it out, put that outside. So that's 8 integral 0 to 1, integral 0 to 1. And if we take the time to distribute this thing times that thing, we end up getting u cubed v plus uv cubed du dv. Now it's just straightforward double integral in rectangular coordinates. So here we go. Pick a new color, why not? If u is the variable, we get 1/4 u to the 4th times v plus 1/2 u squared v cubed, evaluated from 0 to 1. And you can see how pretty these limits of integration are because we simply just plug in 1 and 0. When we plug in 1 first for u, we'll get 1/4 v plus 1/2 v. If we plug in 0 for u, then everything goes away. And don't also forget this is getting multiplied by 8 when we're done too. So what do we end up with here? We end up with 2v plus, oh, this is a v cubed. I almost forgot it. Sorry about that. Plus 4v cubed. Okay, great. And so that 8's been factored in, so I'm not going to do that at the end. I did it now. So finally, integral 0 to 1, 2v plus 4v cubed dv. We take the time to do that. The antiderivative must be v squared plus v to the 4th. I mean, there isn't, talk about a beautiful antiderivative. It shouldn't be, things shouldn't be that easy. And then we'll evaluate that from 0 to 1. If we plug 1 in, we get 1 plus 1, really. We plug in 0 minus 0 plus 0. So we're all said and done. The answer to this double integral is 2. Okay, so thanks for watching. Like I said, what we did was it sort of took advantage of the fact that we already knew about this special transformation that has the property that this weird region we're integrating over, this thing here, whatever you want to describe that as, actually maps into a really nice square in the UV plane when using x equals u squared minus v squared and y equals 2uv. There's really no promise that you're always going to have this beautiful transformation presented to you. So this problem is very specially constructed to give you a sense of how helpful the Jacobian can be. In the next videos, we'll take a look at how do you pick a good transformation given an integral with x and y in it. What would be a good transformation to choose so that you could just, quickly pick out a Jacobian and a change of variables. Okay, thanks for watching.